Let us begin section 10.4, areas and lengths in polar coordinates. Recall that the formula for the area of a sector of a circle is given by A equals 1/2 r squared theta, where r is the radius and theta is the radian measure of the central angle. Consider a curve given by r equals f of theta. Let script r be the region bounded by the curve, r equals f of theta, and theta equals a and theta equals b, where f is a positive continuous function, and 0 is less than b minus a is less than or equal to 2 pi. You can see an illustration of this in figure 2. Divide the closed interval a to b into subintervals with endpoints theta 0, theta 1, all the way up to theta n, of equal width delta theta. This divides the region script r into n smaller regions Ri with central angle delta theta equals theta sub I minus theta sub I minus 1. Let theta sub I star denote an arbitrary point in the subinterval, the closed interval theta I minus 1 to theta I. Then the area delta A sub I is approximately 1/2 the quantity f of theta I star squared delta theta. This is by applying the area for a sector of a circle formula. And so an approximation for the area of script r would be the sum of all of these AIs. So A would be approximately the sum from I equals 1 to n of 1/2 the quantity f of theta I star squared delta theta. The approximation improves as n goes to infinity. In other words, A is actually equal to the limit as n approaches infinity of the sum from I equals 1 to n of 1/2 quantity f of theta I star and quantity squared delta theta, which, by the definition of an integral, is equal to the integral from a to b of 1/2 quantity f of theta squared d theta. Or equivalently, since f of theta is r, a is equal to the integral from a to b of 1/2 r squared d theta, where r is defined as a function of theta. Example 1. Let's find the area enclosed by one loop of the four-leaved rows, r equals cosine 2 theta. So if we only want to find the area enclosed by one loop of the four-leaved rows, we need to pick which loop we want to use. I'm going to use the loop that is symmetric across the polar axis and lives in the first and fourth quadrants. That way, theta is in the interval minus pi over 4 to pi over 4. So, the equation for the area says that I take area is equal to the integral from a to b, so minus pi over 4 to pi over 4, of 1/2 r squared d theta. I'm going to factor out my 1/2, so I have 1/2 the integral from minus pi over 4 to pi over 4. And r squared would actually be cosine squared of 2 theta, d theta. Now conveniently, cosine squared of 2 theta is an even function. So the integral from minus a to positive a is equal to 2 times the integral from 0 to a. So I will take 1/2 times 2 times the integral from 0 to pi over 4. Now to integrate cosine squared 2 theta, I need to use power reducing. So I'll get 1/2 the quantity 1 plus cosine 4 theta d theta. So the 1/2 and the 2 out front simplify to 1. I can factor out my second 1/2. So I have 1/2 the integral. Actually, we can go ahead and integrate. Let's not write the integral. So 1/2, the integral of 1 with respect to theta is theta. The integral of cosine 4 theta will be plus 1/4 sine 4 theta. And I want to evaluate this between 0 and pi over 4. So I'll have 1/2 the quantity. Plug in pi over 4 first to get pi over 4 plus 1/4 sine of pi minus 0 minus 1/4 sine of 0. Well, sine of pi and sine of 0 are both 0. So I'm left with 1/2 times the quantity pi over 4, which is equal to pi over 8. You should have gotten the same answer regardless of which one of the 4 loops of the 4-leaved rows you chose to integrate about. Let's look at example 2. Find the area of the region that lies inside the circle r equals 3 sine theta and outside the cardioid r equals 1 plus sine theta. So we have a circle 3 times sine theta would be a circle living entirely above the polar axis. And then we have our cardioid. So we want to find the area of the region that lies inside the circle outside the cardioid. So please take a look at figure 5 for confirmation on your sketch. So the first thing I need to do is I need to figure out the intersection points for theta. We can do this by setting the two equations equal to each other. So 3 sine theta is equal to 1 plus sine theta. So subtract theta, we get 2 sine theta equals 1, or sine theta equals 1/2. The solutions of which are pi over 6 and 5 pi over 6. Now, I think we should have enough information to set up our integral. So let's try it. Area is equal to the integral from a to b, so the integral from pi over 6. And actually, I'm only going to integrate to pi over 2 because I notice my two side areas are symmetric. So pi over 6 to pi over 2, and I need a 2 out front. Okay. Then I want to find the area of r squared theta, but I have 2 r's to be concerned about. So we have 1/2, just like we did back in Calc 1 where we took upper function minus lower function. We're going to do that here. So it's the upper function squared, so we'll have 9 sine squared theta minus, we need to take our lower function and square it. So the quantity 1 plus sine theta squared d theta. So far I have 2 times the integral from pi over 6 to pi over 2 of 1/2 the quantity 9 sine squared theta minus the quantity 1 plus sine theta and quantity squared d theta. So now it's just a matter of integrating using whatever trigonometric techniques we need. So 2 times the 1/2 will cancel, and I'll be left with the integral from pi over 6 to pi over 2 of 9 sine squared theta minus 1 minus 2 sine theta minus sine squared theta d theta. So 8 sine squared theta, when I combine 9 sine squared theta and sine squared theta, but I'm also going to use power reducing. So I'll have 8 over 2 times the quantity 1 minus cosine 2 theta minus 1 minus 2 sine theta. D theta. This simplifies to the integral pi over 6 to pi over 2 of 4 minus 1, so 3 minus 4 cosine 2 theta minus 2 sine theta d theta. Quick integration would give us 3 theta minus 2 sine 2 theta plus 2 cosine theta, evaluated between pi over 6 and pi over 2. Once you compute this, you should get an answer of pi.